Good afternoon, ladies and gentlemen. Thank you for attending our May 7th Improving Talk. We are thrilled you're spending some of your Wednesday with us. You're joining us for a fantastic series called Integrating AI for Tomorrow's Success. That's right, I said talks with an S. Each Wednesday in May, Improving will feature a different AI expert presenting a unique talk focused on utilizing artificial intelligence to achieve success and create value. Before I introduce our brilliant presenter, who I promise is 100% a real person, I want to ensure that our audience is aware of the QA feature included in the webinar. If you have questions for the presenter, feel free to share them in the QA feature, which is located at the bottom of the window. Your questions will be delivered to our dad joke loving presenter in a timely manner. And since that person loves dad jokes and we're talking about AI all through May, I couldn't resist kicking us off with a quick joke. A machine learning algorithm walks into a bar. The bartender asks, "What do you have?" The algorithm says, "What's everyone else having?" Now, it's a good thing that everyone's mic's muted, or else the huge amount of laughter might throw our presenter off. Speaking of presenters, we are truly blessed today. We have not only one of the biggest dreamers at Improving, but he's also one of the biggest doers. Let me introduce you to my friend Devlin Miles. He's president of Improving's Houston and Austin offices, as well as Improving's chief consulting officer. Devlin will be sharing a webinar titled Architecting for AI Success. The floor is all yours, Devlin.
Thank you, Shervin. I love the joke. Thank you, Shervin. I'm definitely going to be stealing that going forward. So I've spent 40 years working on I, and I'm still not done. And so I don't know how long it's going to take us to master the A as well, but we're working on it. I wanted to dive in a little bit today and talk about how to build for a highly volatile and chaotic world that is AI integration into software and products and those kind of things. I'll give you a little bit of background on me. These are about everything you'd need to know about me as a human, but it doesn't at all tell you why you should care about my opinion when it comes to AI. So let me give you a little bit of that background. So I spent greater than 30 years writing software. The last 20 of that was in high throughput data systems, real-time heuristics from manufacturing, oil and gas, e-commerce. And so working on some incredibly complex, but also hyperscale type problems of moving petabytes and terabytes of data per minute, and learned a lot along the way, wrote a bunch of books, patented a bunch of software in this space. Today, we're going to be talking about kind of the progression of AI and how we can start building down these paths of tooling and structure while not giving up our investment. Because if you invest early in AI and you do it well, that'll set you up for the future. But if you do it badly, you can actually build up a bunch of technical debt that's going to have to get paid down, or you're going to have to start over and re-platform and re-architect as you go forward. So we really want to start kind of walking through what it looks like to build resilient enterprise-grade AI systems. Let's start a little bit with a state of the industry. Right now, the AI space in software development and product development is volatile and chaotic. The overall industry is accelerating at a massive pace. And so when we look at the release of generative AI models or modalities over time, it's only picking up. This only goes through the first of 2023, and we've seen an explosion since then as well. And so we're seeing almost weekly or monthly new announcements, new models, new progression, everything from implementations of supervisors and routers to new models, to new service offerings, to agent systems, to new protocols. And so what we're going to see is this acceleration of chaos and volatility. And we want to insulate from that as we build systems for enterprises, because we don't want what we're building today to be defunct or unusable in 12 to 18 months. And if we're not careful, that's a real possibility. Now, if we look at economically, generally productive technologies, that's the GPT on this graph, these are long cycle changes. And what that means is they typically take a decade or more to impact our industries and our economy pervasively. If you look at electricity, that took about 14 years to really have a significant impact on electrification of manufacturing, et cetera. If you look at personal computers, that's a 28-year cycle when you combine it with the internet, because those were kind of lockstep. And so when we look at ChatGPT and we look at generative AI and we look at some of the stuff coming out from Anthropic or Meta, these are going to have incremental value, right? The value gains on productivity growth is going to stack over time, but we're going to have these new models come out. We're going to figure out ways to use them. And then we're going to have another new model come out that's going to do that job. Plus, it'll have the ability to do several others. And we're going to spend the next decade, probably a little bit more than that, progressively integrating more and more AI throughout the workforce, specifically in the knowledge management space, although AI plus robotics is getting into some interesting things in the manufacturing space. We're going to focus primarily on knowledge work, work that can be done at a computer today. Now, that's the work that's most likely to have AI assistance very, very quickly, but it's also the work that's least likely to be kind of fully replaceable. It is possible with AI and robotics to fully replace like a specific task on a manufacturing floor, but given the complexity and variety of tasks that an average knowledge worker does today, it's unlikely that we're going to see full replacement in that space. Now, I say that to kind of focus us down to where AI is really going to drive. Now, when we talk about building for complexity and designing systems and architecting those systems, one of the things we need to talk about is where the tools make sense. Because you wouldn't want to use a hammer to drive a screw, and you wouldn't want to be using a screwdriver to put a staple into something. We've got to use the right tool for the right job. Now, there's a ton of different ways to build machine learning and AI systems, but largely speaking, they accomplish one of these three things. They perceive a pattern, whether that's a pattern in transactions, a pattern in data, a pattern in language. They perceive a pattern. That's the perceptive. They predict a trend, whether that's the prediction of a stock price or lead time on an e-com delivery, or a recommendation of this is a product you're next likely to buy. Those are all predictive models. And generative is there working with language, the ability to consume and to generate language. That's where the Gen AI and large language model side of this comes in. Now, the thing to know is what we have today is called weak or narrow AI. It's only good at one job. There is not a model that is good at all three of these. We actually don't even have a single model that's good at more than one of these. They are very tightly task focused. And a lot of the value comes, especially in agentic systems, in being able to combine these different types of models and different types of software packages into a combination of things that is much greater than the sum of its parts. If I ask a LLM to do math, for instance, it will not do the math. It will make a statistical prediction of what the math answer should be. Whereas if I can delegate that to a tool that's good for those things, I can actually delegate it off to a math calculation tool, and it ends up working significantly better. And that's really where we're seeing this kind of extrapolation of software design principles, being able to harness these new functionalities without devaluing the design principles that were already there. Now, as we talk about those design principles, the biggest one that we have to talk about when it comes to AI systems is the isolation of complexity. So complexity or volatility, as things change, if you don't isolate it, it becomes significantly higher cost. Giving an example case that we actually saw, which was I'm going to use the initial release of ChatGPT, and I'm going to integrate with it directly against the APIs. Then when I started wanting to add things to that system, I had to code the temperatures and the messaging constructs and everything else. Fast forward 4 months, and we have LangChain and we have some other libraries come out that allow us to orchestrate that. And we're like, okay, we'll reconvert, and we spend all this time and money to do so, but we still lock ourselves into a single model. And then Anthropic Claude drops with the 100,000 token limit. And we're like, okay, we want to use that other one. And that's where things like standards and frameworks and start extracting these pieces of volatility and isolating complexity. So that when I go to build a system today, I have a standard API to almost every model. There's some feature flags of like whether it supports function calling and those kind of things. but it allows me to swap out the model without changing the surrounding architecture. I've isolated that piece of volatility. Volatility and complexity when it comes to AI systems typically come in from the model or from the user interface. The other pieces between it are actually very stable, which is encouraging to hear that those frameworks, technologies, and platforms aren't changing at a rapid pace. And this allows us to lower maintenance costs and development costs because we can really spend our time solving the problems of the business domain and isolate the places where the technology is going to inject complexity or additional cost for us. Now, as we take from that basic idea of an architecture, we want to build it out from that basic to a more advanced structure. So I'm going to kind of dive through this. Now, when we originally started working in the kind of machine learning space at Improving, it was the early 2000s, and we've kind of continued to progress from there. It was rule-based systems. Now we were writing rules and those kind of things, but it was really the rules were coming as an extrapolation of exploratory data analysis. They weren't really machine learning at that point. And we started to then look at decision trees and logistical regressions and being able to recognize rules significantly faster. And we did a lot of this for about a decade. And what we've seen is that the combination of neural networks, machine learning, allowed us to have significantly faster decision systems in those perceptive and predictive buckets. And then you add in the kind of deep learning space for generative AI, and we end up getting all three of the buckets for AI covered. Now, each of those requires a different substructure, a different environment, what we lovingly call ML ops, because you have DevOps and you have marketing ops and you have everything ops at this point. It's our current fad in naming things in technology. And so we have ML ops, which is all your ingestion pipelines, your data storage structures, your monitoring and observability, model validation and gradation. Like those pieces, largely speaking, are interchangeable amongst your machine learning models. Your Gen AI has a little bit different structure to it, but similar basic platform. And so the basic architecture really doesn't change much. This is thanks to one of our AI council internally. They put together a quick, hey, here's rough agent architecture for a RAG system. Now, regardless of which tool you use and regardless of which cloud you're on, this is what you're going to do, right? The knowledge base could be in SharePoint, could be in Documentum, could be in Info, any of those information management systems. Really doesn't matter. What we need to do is the ability to bring in that information and populate an embeddings database of some kind, and then search that knowledge base, retrieve the right documents, add those to the query, and hand it off to a large language model. Every major cloud provider today has this architecture pretty much baked. It's kind of commoditized. You can go into SageMaker or Bedrock in AWS. You can go into ML Studio or Cognitive Search in Azure. You can do the same thing with Vertex and Gemini in Google Cloud. And you can stand this up very, very quickly because the architecture is kind of insulated. The big choices are the two blocks on here. The first is, what's the interface your users will interact with to talk to your agent? That could be a web interface, could be a phone call, could be a text message, but that's your biggest piece of complexity that's user facing. The second big piece of complexity that you have to insulate from is that large language model. Which model are you going to choose, and how are you going to measure and manage that model? Now, models are largely interchangeable, but each platform makes certain models easier to gain access to than others, right? Microsoft, the OpenAI services in Azure, easy plug and play, and they just go. Whereas on AWS, I can use Titan, I can use Claude inside Bedrock, and it just goes. And so each of the platforms has a different smattering of models, but unless you're pushing the state of the art side of it, most of them are going to be good enough. Those two boxes of complexity then give us the thing to architecturally deal with. If I know that my agent or my interface to the user is going to be volatile, it's going to be changing regularly, then what I'm going to do is I'm going to isolate that complexity above an API layer. And so the front end that talks to my chat and RAG retrieval system is going to talk to an API so that I can change that front end as needed. I can plug in a text service instead of a website. I can make inbound or outbound phone calls and have transcription ahead of it. And so what this allows me to do is kind of bundle that complexity and isolate it away from the slowly changing pieces of my code, which is knowledge base and the overall query combinations that happen with the prompt inclusion. Now, as this gets more and more complex, we've taken a more complex agentic system here. You can start isolating things out into where change can happen. Now, the boxes in this are where change can happen. The supervisor allows you to gather data and performs actions. This is going to be the thing that delegates off to tools, right? The router is going to determine the steps of action. And so it's going to go, okay, I need to go take a step. I'm going to hand that off to a specific chunk of this is the tool invocation or expert structure that's going to allow you to interact with really any of your backend IT systems, your existing infrastructure defined inside your environment. So if I have a ERP system or an existing data lake or a Power BI instance, insert ad nauseum other things, what I can do is define a set of actions and an expert that can invoke those actions. Typically, that's going to be querying a database or calling an API or some kind of interaction there. Those are coded. That's not generated on the fly by an LLM. Those are actually coded and then handed to the LLM with a very specific structure around it to say, this is what it is, and here's how you communicate to it. That's the structured output approach. And so as long as the input and output contracts don't change, the behavior of those other systems can change. This is very similar to service-oriented or event-driven architectures from the late 2000s, early 2010s that allowed us to have producers and consumers. You can think of an agentic system as a interface to a bunch of consumption where the producers are those tools or MCP servers is a term you may have heard, and it allows us to pull apart each of those pieces so that we're not having to code all of our downstream dependencies into the model's understanding. The model simply knows I can talk to a system. It doesn't need to know how to talk to the system. We're actually going to provide it the Python code to do that. Now, as we look at pulling these pieces apart, you can see that these Lego blocks can grow heavily, right? They can expand horizontally in kind of big ways because every system that you want to provide as an input source to your AI generative system is going to require that you create one of those expert blocks that it's good at doing one thing. Now, remember, weak, narrow AI, it needs to be good at one thing. I can't give it one tool that goes, you know how to talk to all of my ERP. That would fail miserably. Now, what I can do is give it one tool that talks to a specific API and says, you can pull financial results and you can pull HR data for these specific tasks, and you can pull HR data for these specific tasks. Now, the good news with that is it also gives us fine-grained control because each of those tool blocks isolates complexity, but it also then empowers us to do things like governance, security, monitoring, and that's where that ML ops side of it comes in. All of these outputs from these experts get combined by the action router and then handed off to the supervisor to generate the final response. It may invoke no tools. It may invoke 5 tools. And you don't really need to know as the user of the system which of those it's going to do. Previously, we would have a UI and the user would need to kind of understand step by step the process flow. Whereas at this point with supervisors and routers, what we can do is have the user express an intent, gather enough information from the user to be able to execute that intent, and then go take action on it. Whether that intent is to look up information or if that intent is to take action in an underlying system based on the permissions of the user and all of those pieces, which is how we then delegate out claims or role-based security into those experts. So I'm going to pause here because I saw a question come through. So Ray had asked
Question
the
we have
question.
is how are workflows generated with the siloed AI ML able to create workflows that seem agentic? Speaking a bit of how Cassidy works.
Absolutely. It's a great question. If you take Cassidy, if you take Perplexity, if you take OpenAI Deep Research, like there's a bunch of these systems that look like a siloed model, but they're not. They're actually a pretty well built agentic system that has some default tool invocation. For Perplexity, that default tool invocation is web search. It has the ability to do task delegation. It creates that task list. That's the supervisor to router from this, right? So I make a query, the supervisor or the router breaks that down into a series of actions, and then the supervisor oversees the execution of those actions, and it's going and grabbing a bunch of web research, combining it, condensing it, and it's doing this in a loop. The loop controller that says, hey, am I done yet? Is then delegating those tasks individually, internally to different agents that can take action, whether those are summarization tools, search tools, etc. So what you're seeing in some of those systems that appear to be siloed is that they've actually got an internal agentic structure so that they can task delegate to where the AI is typically very bad at something. Interestingly enough, you see this with OpenAI going back almost 2.5 years now. They've actually open sourced what they call Data Explorer, which is a Python library for analyzing tabular systems. Because they realized that people were asking questions like, hey, here's this CSV file, or here's this Excel sheet, summarize it for me. And the generative system was really, really bad at those tasks, like absurdly bad at those tasks. And so instead of trying to make the LLM globally good at everything, they went, we can recognize when somebody is asking for a task in that space, and we can actually invoke Python, but we'll write the Python from the generative model on how to do it because the generative model is very good at that. But we'll then have a system execute that Python to be able to do visualizations, complex computations, those kind of things. And it was really our first step towards this agentic structure was the ability to do task delegation, which ultimately became part of the tools invocation, tools functionality that exists in most of the state-of-the-art models today. Now, I want to talk about some real-world versions of this because we've talked about how to isolate complexity, but the dangers of doing it badly exist in a big way. So this is an actual example from how we looked at some of the bot structures and stuff like that. We had a few different pieces for a customer. The details are less important. But inside this was their overall architecture. And the idea was, well, we'll just have a bot service that talks to the AI. Notice that that entire bucket is literally captured as one item. The overall application, we didn't want to make AI control everything. We didn't want to make it at the beginning of everything because it turns out it would be a really bad idea to try and recreate places where traditional IT and software development already have a great answer by leveraging AI. What we wanted to do was make sure that AI was applied to the places where traditional software development doesn't have a great answer. Now, we did this by taking off-the-shelf models rather than doing a bunch of research. We didn't go out and build our own LLMs, and we didn't go out and train our own custom language models. We, largely speaking, don't do a bunch of fine tuning either. We do prompt injection, prompt tuning, maybe a couple of few shot examples. Now, the reason that that's important is we actually were able to rewrite an implementation for a customer for about $400,000 ground up, that they had spent over 2.5 million in over 2 years building. And we were able to overcome the issues that they had created in their architectural approach and outperform the existing solution. This is based on a few things. Good architecture is determined by where it puts friction. You want good architecture to make the things that are really bad, really dangerous, you don't want to do. You want it to make those really difficult, if not impossible. And you want to make the things that you do every day significantly faster, easier, more reliable, etc. By shaping the architecture to the problem space and having our evaluation criteria on the models built into that architecture, we could prove the off-the-shelf large language models could outperform the custom-built and fine-tuned ones because we were able to measure that. And we were able to swap out the models and test different versions of it. Now, this is important both for evaluation, but also for growth. If I know that Claude 1 is dropping and fast forward 2.5 years, we'd be on Claude 3.7, I know that I'm going to need to keep that model at the middle of my architecture interchangeable. I'm going to need to be able to swap it out and evaluate. Did it get better? Did it get worse than the previous version for my specific use case? And so we build into the baseline architecture the evaluation criteria for each of these models. It's a part of that underlying ML ops approach that we talked about. Hey, I'm going to throw this up and I'm going to have Python running in an Azure app service that invokes directly against the models. You can do. But unfortunately, what you're doing is you're trading a ton of risk to when those models upgrade, your users may be the ones coming back and going, hey, your system just suddenly got worse. And you wouldn't know it. We actually have a client that we do a lot of generative AI work in a complex scientific space. And we are constantly evaluating new models to see for this specific set of tasks, do we need a different model? Because it turns out each of the different large language models come with their own bias and style and knowledge base from their training systems. Some are better at certain tasks than others, like comparative analysis tasks between two sets of text. There are certain models that perform better than others. Generation of marketing content or creative content or summarization, some perform better than others. By creating an architecture where the model is interchangeable, what we've also done is create an architecture in which we could vary the model by task. And that allows us to achieve a significantly higher result set without a significantly higher result in performance, accuracy, et cetera, without having to recreate the overall architecture. Now, the way improving approaches this is experimentation. Now, experimentation is different than just doing things. We take a very clear and methodical approach. I'm going to take everybody back to like fifth, sixth grade science class. An experiment requires a hypothesis. It requires a rigorous methodology or scientific method. It requires control, and it requires publishing your findings. And so we try and hit all four of those major things when we talk about architecture for AI. The rigorous approach is that underlying measurement evaluation harness. There's a structure in generative AI specifically, but it also exists in machine learning models in which you have what's called model drift. You release a model and a system into production, and over time, the model just gets worse. Now, this model drift is caused by a couple of things. One is that language changes over time. How we talk, how we interact, terminology, vernacular, all of those things change sociologically. And so we actually get worse at talking to a model that doesn't change after it's been produced. And so that point in time, as the distance gets greater between when it was published and today, we actually see diminishing results. Even though the model was good at the task 16 months ago, it may not be good at the task now. So you have this kind of need to have a rigorous method for evaluation, even if you're not planning on swapping out the model. The second piece is the hypothesis. Can we do X, Y, and Z faster, easier, smoother, cheaper, whatever the terminology is, with an AI than we can with a human? The idea behind it being that we can take certain tasks off the human's plate that AI is going to be very good at. But we really haven't defined what those tasks are as a civilization yet. There are some tasks that AI is phenomenally good at, and especially generative and predictive AI. There are some tasks it's phenomenally bad at. Every single chat system out there has a disclaimer, may get facts, dates, etc. incorrect. Make sure to check the results. This is because it's very bad at determining truth. There's no math equation for truth. And so we have to add that discernment as the human user. If I start delegating off my critical thinking to the computer, there was a recent sociological study by Harvard published, said that self-reported number of people that use AI for critical thinking tools like OpenAI, et cetera, for critical thinking tasks, they actually saw a decrease in critical thinking ability within 6 months. And so as we just hand off some of these things, we get worse as the humans. And so we got to find that interaction style. Now, once we've got this and we've measured it, it's important to publish the results because trust in an AI system is largely based on whether I trust its results. If I can publish a 91% accuracy rating to my users in some form or fashion, I'm not saying you like put it on the screen and be like, we're only right 91% of the time. But if I can publish that to them in a meaningful way, then it's like, well, 91% of the time it's going to be accurate means I have an internal expectation of 9% of the time I won't be accurate. And so I need to pay attention to it. And that's where those kind of structure of experimentation actually helps us to accomplish the end goal. Now you'll notice we've talked a few different times about qualitative measure as well as quantitative measure. User feedback, and this is very common, right? The thumbs up, the thumbs down, the copy button, etc. on generative AI responses, those are feedback systems that allow for iterative progress and refinement, very similar to click-through rates on websites and those kind of things. A user's feedback is a precious commodity, especially when you're talking about how to continue to capture the user interactions and make the job and the task that you're working on more effective. A baseline architecture needs to include those feedback mechanisms. Now, the good news is there's plenty of tools, technologies for this, everything from Adobe Experience to a open source TypeScript library. You've got a bunch of different options in this space. The quantitative metrics on model performance, latency, response time, token throughput, those are getting baked into the platform. And there's some good platforms that kind of handle all of that for you. Or there's some kind of build your own platforms that are more infrastructure as a service for AI right now. The hyperscalers, Google, Microsoft, AWS, are largely going to be kind of in between. They're going to have more than the pure play, I'll just run it on my GPUs, but they're going to have less than the managed service platforms that's pre-baked for you. They will be lower cost than those fully managed platforms when it comes to the operating costs, but they're going to, they're going to require some wiring. And so it's about where, as a company and an IT group, you really want to go is going to determine which of those architectural directions you go. We actually choose both at Improving. We have some AI platform work that we do on the generative side of things that goes into a fully managed platform. And then we have some stuff that we've built and wired together because it's a core part of our infrastructure. It lives in Azure. We did the wiring together for it, or it lives in AWS, and we did the wiring together for it. And we've owned that maintenance and that platform cost because we wanted additional flexibility that a managed platform wouldn't give us. So it allows us to fine tune that. Now, let's talk about where it goes from. You've got a basic architecture, you've got qualitative and you've got quantitative measures, you've got your complexity isolation for your user interface and for your model. Where does it go from here? As we scale up agent systems, right? Agent is simply a user interface over a generative orchestration. As we scale this up, we're going to find a few different things come in. Now, Google announced the A to A protocol. Anthropic defined the MCP protocol, which was an evolution of the tool calling functionality released by OpenAI. So everybody's kind of contributing to the growth of these different patterns. But something I want you to notice is these patterns follow human sociological benefits. What I mean by that is humans invented tools so we could do things that we couldn't just do with our hands. That's the same thing that happened with tool invocation for large language models is we gave them tools for the things they were bad at by general. So we give it a tool for analyzing CSVs or tabular data, these kind of things. And so that's the MCP thing is going, I have a toolbox in my garage. Here are all the tools. It determines what jobs I can do. If I don't have the tools to do the job, I either go to Home Depot and buy a new tool or I don't do the job. Those are my choices. And so that's very similar to the way we're going to equip generative AI is we're going to architect it so that it has a toolbox and it knows what tools are in the toolbox if your kids didn't put them where they're not supposed to be. And then you know which jobs you can do. And if I get a request from a user that's for a job I don't have the tools for, I tell the user no. Now, the A to A protocol is the next step in that. It is literally creating the ability for agents to collaborate on a task. Like, well, I don't have a tool, but my friend Shervin, who's our producer today, he has that tool. So I'll call Shervin and see if I can borrow the tool, and Shervin will bring it over, and him and I will work on the project together. That's the A to A protocol, is the ability for agents to interchange between them conversations, UX negotiation, capability discovery, etc. And so what you're going to see is very similar to the service-oriented architectures of the late 2000s, early 2010s, the event-driven architectures of the mid 2010s, to the microservices architectures that we're seeing late 2010s to early 2020s into real-time event streams that we're seeing currently. You're going to see this growth of agents talking to agents and each of those talking to tools. You still need the tools built around the edges of that architecture. And largely, these are still going to follow the sociological patterns of humans collaborating on tasks and the technology patterns of systems integrations for making two systems talk to each other. And so that baseline understanding of integration patterns, design patterns, et cetera, will apply even into the AI space with a little modification to how we go about those. The protocols will change, but overall, computers talking to each other is something we've been very good at as an industry for 30 plus years at this point. Now, where do we go from here? So we've talked about how to architect now. We're going to talk about where are we going from here. Now, we're going to get to proactive AI. I was actually with a group yesterday in Austin talking about how real-time data platforms that capture events that come across are going to become more and more important at a more granular level. Because as I contextualize everything a user is doing in my application, having all that information applied to and handed to an AI system so that it can constantly be thinking and working like a sidekick to the human means I need information coming in onto that event stream or real-time bus or whatever you want to use there, and be able to then have the AI proactively engage the user rather than almost all the design systems today are reactive to the user. The user asks a question, the user does something, and we procedurally invoke the AI. Imagine the AI literally as a co-pilot who's sitting right next to you, watching everything you're doing and going, hey, did you mean to do X, Y, and Z? I can speed you up on that. And so what you're going to see is this kind of real-time data platform need enter most of the AI architectures that are developing. The anticipation of errors. We're, as a civilization right now, trying to come up with frameworks for emergent failure and the ability to mitigate those failures, either through proactive intervention, where a failure happens, the computer responds and then notifies the user later, if ever, or prevents the user from taking an action that it knows will become a failure because it's got more context than the user. So we're going to see some of those things. But in all of these, we're going to need the ability to have feedback loops and to be able to kind of adapt our architectures in modularity. And so very similar to the microservices and modularization that we've been experiencing as an industry for the last 10 years, we're going to continue to see that grow into the AI space. We're also going to see that the MCP and AA architectures are going to allow us to harvest the investment of our existing IT infrastructure. So I'm going to have MCP servers or function calls that sit on top of my existing systems and know how to interact with them. And then I'll have an agent structure layer that allows me to then interact with those different systems. I'll probably have agents that are role specific. This is my business analysis or my finance agent. This is my payroll agent. This is my budgeting or accounts payable, accounts receivable agent. Under the covers, it'll have MCP servers or tools that allow it to record checks or invoices. Like it's going to take tasks that are specific to that role. And then we'll have projects or programs or things, or scenarios that require multiple roles to be involved. And that's where the agent to agent protocol is going to come into those architectural designs. But we'll see that in the future proofing and isolating for complexity is that role to task breakdown. It's going to seem very similar to coordinating and managing a group of people. You're just organizing and managing a group of computerized labor. So pausing here, because I saw a question come in. Shervin, what was it?
So Alan is asking, so is A to A better than using MCP? In other words, how do we orchestrate multiple agents working together without MCP?
It's a great question. So let me go back here and talk about it. So MCP servers are the ability to interact with something. They're effectively a tool call to a third party system, et cetera. Now, those MCP servers can, under the covers, be another agent, but the A to A protocol actually enhances that interaction. So what I would say is right now, A to A is a fairly new thing, like very new thing to the industry. But what we're seeing so far is you're going to have role specific agents, and then you'll have MCP servers that you're talking to accomplish specific tasks in that role. And when you have two different agent roles that need to collaborate, that's where you'll see the A to A protocol. Largely speaking, there'll be a layer where you'll have supervisory agents who are using A to A protocol to coordinate the individual contributor agents. Very similar to how you see team hierarchy and structure exist inside human organizational structures. So it's not that one is better than the other, but that they accomplish very different tasks.
Charles mentions that MCP and A to A seem to complement each other.
Absolutely. And they were built to do so, right? So when we look at like the function calling that was originally there, it was very like individual task centric. MCP servers created a plugin or just the toolbox approach, right? Like imagine that function calling is you're always carrying around a hammer and you know that you can do jobs that require a hammer. The MCP server went, I'm going to give you a toolbox and you can load it with whatever tools you want. And every time I get a job, I'm going to go look through the toolbox and see if I have the tool for the job. Then the A to A protocol is building the team of people with different toolboxes that can accomplish a bigger task. And so the idea behind this is that we're going to continue to have these abstraction layers discovered over the next probably 5 to 10 years. We're going to continue to discover new frameworks, patterns, abstraction layers, very similar to the or the object-oriented programming transition or the JavaScript and jQuery to Knockout and Backbone to Angular to React evolution, where we continue to find new abstractions, new modularizations, new patterns. We're going through that evolution with AI. And it's going to take a long time because you have to build it wrong a few times before you find out here are the common patterns to doing it right. Now, I've touched on a ton of topics today. And I want to kind of pivot now to tell you how we're going to dig into more of those. Because this was overall how to architect, how to approach the problem, how to design for the complexities that you're going to deal with. We're going to deep dive 3 of the big areas we talked about today. So next week, David Belcher and Michael Slater are going to have an amazing conversation about the new user interaction paradigms that are showing up for intelligent systems. Keep in mind that the entirety of the software that's been built today has been built for very few interaction modalities. Keyboard and mouse, right? Originally, it was all keyboard, command line. And then we added the mouse, thank you, Xerox, and the graphic user interface, and that got us there. Awesome. And then we got to the touch screens for phones, tablets, etc. And that's really it so far. When we add generative, things like text to voice allows us to have conversations with systems, but they're also non-deterministic. If a software package did something differently each time, we would report a bug and say that software was broken. But generative AI, it's going to be different every time because it's going to regenerate with some creativity, et cetera. So we've got new user experience design happening in real time. Our industry's discovering these. David and Michael are going to dig into those and really have a great conversation. Michael from the technical solutions architecture side of it, David Belcher from the user design and information architecture side of it. That one's going to be a barn burner. I'm looking forward to it. And then Scott Poulin talking about complex problem solving with AI. What we touched on from that very basic to more advanced, Scott's going to pick up from there and go, let's talk about how AI layers into these complex enterprise level software packages and how new functionality can be built into those without having to rebuild the world. And then finally, Kevin Jourdain out of our Atlanta office is going to be talking about as agents become more prevalent, how do we focus them on doing the right things at the right time to help the humans accomplish a job? It's really going to be this collaboration of agents and humans and tools to save time. So he's going to really be digging into that topic and kind of looking at what organization and work design is going to look like in this space going forward for the next few years.
Thank you, Doug.
pending questions as we look to wrap up the day.
Do any AI bots have questions? We take those too. Thank
Awesome.
you all for attending today's Improving Talk. And Devlin, thank you for sharing architecting for AI success. We appreciate your dedication and generosity to the IT community. The recording of the session will be available the next business day. Locate the session from Improving's virtual events page to view the recording. And while you're on the Improving's virtual events page, make sure to register for future Improving talks, including the other AI talks that Devlin mentioned a second ago, that are all part of our series called Integrating AI for Tomorrow's Success. Thank you and have a wonderful day.